You know how your email just seems to know what's spam and what isn't? Or how a computer can learn to tell a cat from a dog? Well, a lot of the time, it all comes down to a deceptively simple idea, drawing a line to separate one group of things from another. But that simple idea opens up a really fascinating problem. I mean, really think about it. You could draw a literally infinite number of lines to split two groups of data. So how does a machine with no human intuition pick the one perfect line? The one that's going to work best not just for the data it's already seen, but from new stuff it's never encountered before? That's the big question we're going to tackle. So let's start by looking at this problem up close. We'll call it the classification challenge, and honestly, it's right at the heart of what makes machine learning so powerful. Okay, so picture these dots. They could represent anything, really. Spam emails versus good emails, pictures of cats versus dogs, or even something as critical as healthy cells versus cancerous ones. Our job is to teach a computer how to tell them apart. The most obvious way to start is to just, well, draw a line right between them. And there you have it. Problem solved, right? All the orange dots are on one side, all the blue ones are on the other. But not so fast. Take a closer look at that line. Yeah, it works, but it's kind of hugging those orange data points really, really tightly. And that's risky, because if we get a new orange data point that's just a little bit out of place, our line might get it wrong and call it blue. That's not very reliable, is it? All right, fine. So what if we try another line? We'll swing it the other way. Now, we've avoided the orange group, but we've got the exact same problem on the other side. It's way too close to the blue dots. We're still running that same risk of making mistakes down the road. So clearly, we need a smarter way to find the optimal dividing line. And that smarter way, you guessed it, has a name. It's called the support vector machine, or SVM for short. And this is the brilliant algorithm that was designed to solve this exact problem with a surprisingly simple and really powerful idea. The SVM is a true powerhouse in the machine learning world. It's an incredibly versatile and effective algorithm, and it's famous for solving exactly the kind of classification puzzle we've been looking at. Now, before we get into the magic of how the SVM does its thing, there's just one little piece of jargon we need to pick up. In machine learning, we don't just call this dividing line a line. It has a much cooler, more official-sounding name. It's called a hyperplane. Now, I know that sounds super complex, but it's not, I promise. In our little 2D example here, the hyperplane is just a line. If our data had three features, like height, weight, and age, it would be a flat plane. And if it had more dimensions, well, it's a hyperplane. It's really just the universal term for the separator that splits the data. Okay, so the SVM needs to find the absolute best hyperplane out of all the possibilities. So how does it do it? This is it. This is the big aha moment. It's the core idea that makes SVMs so incredibly clever. The whole secret is a concept called the margin. The margin is basically a buffer zone. A great way to think about it is like a street running between two neighborhoods of data points. And the width of that street, it's decided by the houses, or in our case, the data points that are closest to it on both sides. And there it is, the central mission of the support vector machine. It doesn't just look for any line that separates the data, it hunts for the one single hyperplane that creates the widest possible street, the biggest buffer zone, the absolute maximum margin between the two groups. This gives us the most confidence that we found the best, most stable boundary. Now, those specific data points that sit right on the edge of that margin, they get a special name too, support vectors. And they are the most important points in the entire data set because they alone support the final position of the hyperplane. You could move any of the other points around and the line wouldn't change one bit, but if you move a support vector, the whole solution has to change with it. So, let's just lock this idea in. When you boil it all down, it comes to this. The best, most robust dividing line, that optimal hyperplane, is the one that pushes as far away as possible from the closest points in each group. It is all about maximizing that empty space, that margin. Okay, this is a really elegant idea, right? But what does it mean in practice? Let's take a look at why finding this maximum margin separator is so unbelievably useful out in the real world. Because this concept of finding the clearest boundary is so powerful, you see SVMs pop up everywhere. They're used in facial recognition systems to tell one person's face from another. In medicine, they're helping to classify cells as cancerous or benign. They're used to categorize news articles and to sort all kinds of images. Pretty much any problem that boils down to finding a clear boundary between groups is a perfect job for an SVM. And that kind of leaves us with one final thought to chew on. Our world is full of messy, complicated data that often overlaps. So, in that context, what's the real value of having an algorithm that is obsessed with one thing and one thing only? Finding the single, clearest, most confident boundary it possibly can. It's a really powerful idea, and it's what makes the support vector machine such an essential tool for making sense of our complex world.